Thanks a lot for the nice introduction, and I also want to thank Panjeo, the team, the entire community to invite us to present our work here. That's today, that's me, Gunnar Brandt, and Norman von Ferrer, who is the lead developer of xcube. So the title is xcube, a simple one, Python package for Earth observation data cubes. We take this opportunity here today to try to also give some background how we got to develop such a software package, who we are as a company developing this software since some years now, and giving some examples. So that's a pretty dense plan today, I have to say. So I try to start right away and speed up a bit in the beginning. As I said, that's the introduction, not to the software, but to the company behind it, since we are newcomers to this series here. We both work for Brockmann Consult. It's a small limited enterprise located in Hamburg, Germany. We develop open source software for the exploitation of environmental data, and that's mainly Earth observation data, so from satellites. We provide consultancy and geoinformation services with this software, but also with other software that is not developed by us. And we have a diverse range of customers from space agencies, European institutions, but also local and regional institutions dealing with environmental information. That's all summarized in this image on the right. You can see that from the left, from ESA and NASA and EUMETSAT, so the big space agencies, and from left to right, it's going downstream. Copernicus Services is a large customer of ours, and on the right, you may notice that this is a larger national environmental agencies that are all having a demand and requirements for environmental information. And our job or objective here is to bring this information further downstream to the customers. So we take Earth observation data, build software, provide services with this data, and enable our customers and users to exploit this data as convenient as possible. So now just two examples of what we've been doing besides xcube. This is probably one of our flagship software, Snap. We are lead developers of this Sentinel application platform for ESA since 2014. That's the standard software for accessing, processing, and analysis of Earth observation data, mainly from European sensors, but also from others. So that's a pluggable architecture, and also NASA satellites and others you can work with in this software. It contains a visualization component, a lot of analysis functions. There's a graph processing framework for large-scale processing, and a lot of geographic specific functions. We have a large and active user community. The forum is the main exchange interface for us with this community, and we have 8,100 registered forum users, and I put it somewhere up there, 190K downloads for the current version only. And ESA is continuously supporting this software. So that's one of our main software involvements before xcube, and another one is Calvalus is closely related to this. It's a batch processing system for Earth observation data based on Hadoop, and the typical task of full archive processing of satellite data. We started this on premise. It's now also capable of working in commercial cloud environments. You can plug processors like these Snap operators, but also other Python programs, Unix executables. It's pretty versatile tool, and we have some institutional customers in Europe also for this. It also supports, of course, NetCDF as output, and quite recently we added zarr support and others. So for xcube, there's a also quite longish history when I try to trace this back to the beginnings. It started even before I joined this company. So there was a Fringes initiative in 2011. It's a Frascati initiative on global empirical analysis of biosphere and Earth system, which is already shows that it didn't really start in this data science community, but with Earth scientists who had very clear requirements for their research. This initiative then was turned by ESA into the first project, CouplUp. That's where we joined the Coupled Atmosphere Biosphere Laboratory. So there we created a first data cube from multiple data streams, many from Earth observation, but also from other sources like model data. The follow-up was Earth System Data Lab, again in ESA project, which was completed just recently. And in parallel, we had a European Commission project, which was called Data Cube for Copernicus Services. And that was where we actually took all the lessons learned from these previous projects and had a first version of xcube, which is the main subject today. So let's say the common requirement, the common objective in all these activities was that we had to build a multivariate analysis ready data cube from several heterogeneous data sources and enable the users, in that case, Earth scientists, to do their empirical research. So that's where it all started. I think that probably sounds familiar to the Pangeo community. So that's a common requirement nowadays, and I think that's also what we share with Pangeo and other initiatives. So going a bit more into detail, these common objectives of these projects were that you need a convenient access to as many gridded data sources as possible. That's a very tedious task for many researchers. Then generate from this analysis ready data so that they can readily be used in these empirical contexts. High level tools and functions are needed to exploit and manage these cubes. And then, at least in our project, there was always a service component. So serving these data, visualizing data, analyzing surf data. And in one of these projects, you will see later, we even had a requirement or have a requirement for a toolbox as a service. So that these requirements led us to take on this task to develop what we call integrated cube ecosystem. Maybe ecosystem is a too large word here, but what we are working on at the moment sometimes feels like an ecosystem of different modules that fit together and hopefully make our and other people's life a bit easier. And we are heavily the task on the known packages xarray, zarr, dask. So that's the common ground we all stand on. So going a bit into technicalities, xcube components and features, we have a data store framework for the data cube access. It's a Python API for existing data web APIs and storage types. It creates lazy data cube views, which is a very useful feature. And these data stores can serve cubes, also multi-resolution cubes and vector data. So we also have a GeoDB that serves vector data because that was one specific requirement in the service. One of the main components is a generator, so which creates from NetCDF, but also from other data stores, zarr data cubes. So we write zarr cubes to local file system or to S3, which is the most common use case for us. Yeah, and you will see later that in this generation step, you can also execute user code so that at least if a user needs it, you can forego this redundant saving of input data in a cube format, but just save the product of this processing. So we have, I mentioned this before, a lot of other, let's say, downstream components in xcube server. We can serve data from a local file system, from S3, from any other data stores, tile catalog and time series extraction via REST API. So we are working on the OGC stack catalog, which will come in the future. There's a OGC WMTS support by the server. But we can also emulate an S3 REST API through this server. The viewer we will demo later uses this server and displays cubes and vector data on a map. For us, that was a very important feature that many users and customers like a lot, because it works directly on the cubes and doesn't store pre-computed image tiles. You can have we can go through the time stack of images or plot time series diagrams, and also vector data can be integrated. There's a cube CLI and a core package, which is the high-level computation analysis and management, contains these high-level computation analysis and management tools, and the CLI particularly is important if you want to automatize different steps. And Kate, the let's say most sophisticated backend, which uses xcube in the back, is a toolbox as a service for the ESA climate change initiative. It actually doesn't really work on data cubes, but on ZARs, but it's compatible also with data cubes because yeah, they share the same specifications. How does that look like? I think this is the most useful sketch here. So on the bottom, you have different pluggable xcube data stores. You see the ESA climate change open data portal API, Copernicus climate change service API, the Sentinel Hub, which is a commercial service we use a lot, and other products on S3 or on FTP. You may also add many more if needed, and then you can plug it into xcube. So there's an xcube service deployment layer, which we use for many of these projects. There's an xcube generator as a service, and the server that takes the resulting cubes and can serve them, and the viewer on top of it can display them as a web service. But this arrow on the left shows you that you can also use the data stores directly to access from xcube, from a programmatic environment like Jupyter or in your any other Python program, these data sources, and then you get immediately data cube views from these sources. Data store examples are, for example, the ESA CCI Open Data Portal, the Copernicus Climate Data Store, or the Sentinel Hub. You see on the right this example, which shows how simple and convenient access is then to, in that case, to a full archive of Earth observation data. You create a new store here. You list the data IDs in this store. That's the commercial Sentinel Hub service. It provides you Sentinel-2 level 1C, Sentinel-1, Sentinel-2 level 2A, and DEM. And these are the data stored on AWS in this case, and they represent the full archive of these sensors, which is a couple of petabytes in that case. And then you can open that store. In that case, the surface reflectance is level 2A. You have a bounding box, a spatial resolution, your coordinate reference system, and a time range, and the time period. So in that here, 1 day. So you want daily time slices, and that's the lazy view of this full archive. So this 10 time steps, lat and lon dimensions, 2,000 times almost 4,000. Grid points, and that's you can see at the dask array, so that's a lazy view on it. So that's really shortens the way from to actually accessing and working with the data compared to downloading, getting, preparing, all these kind of things. So the generator is one of the main components we have. You may further separate in different steps, and they are all represented also by a configuration. So you need an input config to select the store you want to read from and you want to access. There's a cube config that configures the the specification of the cubes. So you might subset, resample, and combine. A code config if you want to apply user code, so directly at this generation step, and you need an output config to define where to store the result. So in S3 in that case could also be local file system or memory or whatever. So that's now the time to go to the first demo, which is a Jupyter notebook. Let's switch here. Okay, there it is. That's a simple Jupyter notebook. You see here, I'm in this Eurodata Cube Jupyter Hub. That's an ESA project that develops this Eurodata Cube service, which is a commercial service. So we're just using for the demonstration here this environment. So we start to generate our simple example by defining our bounding box. That's Hamburg. Norman and I are actually within this box at this moment. I can also run all just to show you that it works. So we are here at I think that was I restart the kernel. I'm not sure if it started here in the first. No. Okay, we're here in this bounding box. That's a small bounding box around Hamburg. We load some xcube packages and we start configuring our cube. Just as you've seen in this scheme, there's an input config. We again use the Sentinel 2 level 2A. We configure our cube config, so the variable names. In that case, it's the bands 2, 3, 4, 5, 6, 8, the scene classification, and the cloud mask. We can give it a tile size, the spatial resolution in lat.lon, the bounding box we defined above, the time period every 4 days, and a time range, which is rather small here, just to make this run through in during the demo. Then we have an output config. We just want it as a file, and the name of it is Hamburg, the source cube, and the zarr. So then we build a request from this. We stick everything together. You have now here the input, the cube config, and the output config. So that's fully defined. We import the generator class and we instantiate the generator object. And now we can get the cube info. So its status is okay. And we have a size estimation here, a number of requests, for example, tile size, image size. So it's before you start generating the cube, you get the info, how big it will be. The image size is the tile size we defined, the number of variables. So everything there. If you're happy with that, we can generate the cube here. So we stick the request into the local generator. And what we get is a result, hopefully. It's now still running. It took, at least in the test, 118 seconds. So there it is. I'm a lucky guy. And we can open our result, and here's the cube. So that's lat.lon time, as expected. It's a nice xarray data set. So even with some metadata. Now we want to develop an algorithm. So that's the source cube, band 5. You can visualize it. You can display it. That's the city of Hamburg, the river Elbe. You can see here. So it seems to be fine. We can use here an xcube function to explore the mask set we have here. So we need, of course, to mask water and vegetation. We need the mask sets from the satellite data. We can look at the water mask. It's again a cube. The vegetation mask, it's a cube. We can explore it. We can visualize it. That's all there. What we now do, that's, let's say, a small toy example. We code an algorithm. In that case, these are two indices. The one is an NDVI, which is well known probably. I don't have to explain this. And this is an equivalent for the water thematic area is a maximum chlorophyll index, which is also a simple band mass. So we define it just by a simple Python function. We have now a compute MCI variable and a compute MDVI. In the next step, we define our compute index cube, which uses these compute MCI and NDVI. There's the inputs from the cube band 4, 5, and 6. And there's an output, and this is in the end an MCI and an NDVI, and we stitch everything together into a cube that is returned then. Here's MCI and NDVI as new variables. So that's plain Python. That's, I think, very attractive to many natural scientists because they can simply code their functions in the environment and in the program language they know. And then we can compute this our cube given the source cube that we just downloaded. And if we do this, you see down here MCI and NDVI are inserted as two new variables in our source cube. So we can now check. We can display this NDVI. Looks fine, quite greenish, but it's Hamburg. It's quite wet. We can look at the MCI. It's also looks nice. You may note here that the masking has worked quite well. So the MCI is only computed over water, whereas the NDVI, well, you cannot see this, but it's only computed over land. So that's exploiting the mask in the product, in the original product. Now we package this algorithm, so we put all together our functions if we're happy with them and our algorithms into this code config, and we just put in the functions we defined before, and we name this module index processor. And this here is we test if this works. So we call the code config get callable, and if this is valid, everything is fine. So once we have that, we can test if you can also generate. We can test if we can generate everything together. So get the cube and compute the MCI and NDVI. So we request here with code, and we have a new cube generator request with input cube config, code config, output config. And in the end, we do the same as before. And I just speed up a bit. I think if you do so, you can, in one go, let's say, generate a cube where you have your additional new user code computed variables in there. So that's a full cycle, if you like. You can see that it worked as well here. And the last thing I will skip, just to mention here, we implemented this also as a service. So in Eurodata Cube, because this has been done locally, we also set up a service that works the same. So there you have an endpoint and then a client and a secret ID, and you can simply submit via an API your request, and the service will generate this for you. But this is, I think, maybe not the most interesting here. This for this presentation, and given the time, I will go back to my presentation. So it was the first example we looked at. So we computed this cube over Hamburg with MCI and NDVI. The second example is actually quite closely related because that's involving the viewer, the xcube viewer, where you see the same, or a bit bigger area of interest and these two variables in the viewing service. So if you go back, we have the viewer here. So you may realize that's Germany, Europe. So Hamburg is in the north of Germany. I zoom back in. is a bit slow at this moment. So what you see here is band 4 of what we called Hamburg City Cube. You see some clouds, and you see the surface reflectance values of band 4. If you click here, you can also see that there are more of the other variables. In that case, of course, the bands and this MCI and NDVI that we just computed. You can switch on RGB, and then the RGB is computed from these bands 2, 3, and 4 here. So since we have them, we can also on the fly compute an RGB and toggle back. But of course, what we are really interested in is this NDVI, and you can see it here. And if you now click somewhere in this image, then you will immediately see a time series, and you can also go click on a point in the time series and go back to the image. So that's directly working on this zarr cubes. You can, of course, have the maximum chlorophyll index, which looks different and then only shows the water areas. So we have to, I think, adapt here a bit the color range. So that's the famous small lake. We have some other convenience features here. You can draw a polygon, and then well, that's I close this and I draw it again because that was in the same figure as the NDVI, they're both unitless. So then it calculates on the fly the values, the mean values for this area, and also the standard deviation in that case. So that's a very useful tool for us. We use this a lot because many users and customers like this to have an immediate view on the data. You can also, that's the last thing I will show here, go through the data and in an animation. Okay. So last thing, last example, I won't go into detail now. I just wanted to mention that it's also powered by xcube in the backend. Is the CATE, it's called the Toolbox as a Service for ESA's Climate Change Initiative. So there we analyze essential climate variables provided by the project. Most of them are also from Earth observation data, but they are not in a strict sense data cubes. There are numerous data sets here. You see it on the left. There are also numerous functions. You can add additional functions just as Python functions. You can define workflows, and of course you can visualize everything on the globe or as time series. So that's currently under development. It's a free web service, also supported by ESA. If you look a bit into where this is used in terms of projects, so I just selected 3. So we have here Cyano Alert. It's a cyanobacteria information and notification service with several public customers in the Baltic region in Sweden. It uses also the viewer, but also has a mobile app and sends notifications. Eurodata Cube, you've just seen in action, if you like. It's a larger initiative, also together with other companies. It's ESA's flagship data cube project, if you like, and we use and further develop xcube here. And we just recently started Agriculture Virtual Lab, which is a virtual laboratory for researchers, mainly working with Jupyter. Also there, the objective, the requirements are making available a lot of relevant thematic data for agriculture researchers. So you see the xcube development as such is supported by a lot of activities we have. The road ahead is well, it's a long road ahead, we realized. So we started from a very clear starting point and requirements, and then we extended what xcube is on various ends. And of course, there's still a long road to go. We have here a lot of additional features we're working at for example, arbitrary spatial CRS, large-scale batch processing, catalog service, multi-resolution pyramids, improve the resampling that we have, enhance the OGC support, and add machine learning and AI capabilities. Many of these things I'm pretty sure are familiar to many of you because it's common requirements, common issues we all have. We also always wanted to evaluate in greater detail, in more depth, other initiatives and software projects like Pangeo and Open Data Cube, because we realized that there are a lot of things that are developed in parallel with similar functionalities, and I think we could benefit all sides from reusing rather than reinventing. Improve documentation, which we indeed have to do, and give a bit back to the open source community, which we benefited a lot from. Okay, you can find us, of course, or the source code. It's on GitHub. It's still under the CCS for COP, under the project repository. It's still in there. Xcube is licensed under MIT license, so it's basically free to use and to modify. You can, of course, submit pull requests if you want to contribute or have any issues with the software. You can install from Conda Forge or simply write us a mail. That's, of course, we are always happy to hear about users or other users that we are not aware of so far. Yeah, and I think I started with a thank you for inviting us, and I think I have to really also finalize this talk with a big thank you to this open source Python community, particularly to this, let's say, the core packages Xcube is using and based on xarray, zarr, numba, and dask, but also many others, numpy, pandas, a lot. So this software would not be possible, would not exist basically without these other great packages and the commitment of some of you in the call, but also many others outside. Thank you.